Hello, everyone. Today I'll be talking about three stochastic problems: the secretary problem, the profit inequality problem, and the stochastic probing problem. We'll study these three problems under very general downward close constraints under the same unifying lens, which we'll call the big decisions first principle. So my name is Sahil Singla. I'm from Georgia Tech, and this is joint work with Aviad Rubinstein from Stanford. So let's look at the high level, the general packing problem. So what this talk is about. So by general packing problem, I mean like you have n elements and each element has a weight, some non-negative weight, and you're also given some downward closed feasibility constraint. The goal is to select a feasible set of largest possible. So every element has a weight and you want to select a feasible set to maximize the sum of their weights. And this captures classic problems such as matchings, selecting max weight independent set in a matroid or independent sets of a graph. But the crucial thing is we'll make no assumption about this downward closed set system. It could be an arbitrary downward closed system. It need not have any matroid structure or intersection of matroid. It's an arbitrary downward closed set system. And the objective is to select the max weight feasible set. And often for these packing problems, they are easier to solve in the unweighted setting. So compared to the weighted setting, by unweighted setting, I just mean that the weights are either 0 or 1. So basically, if a weight is 0, you kind of like offline, if you know all the weights, then all the 0 weight elements, you'll just discard them. And it's really about just maximizing the cardinality or the size of the feasibility set that you'll select. And often it's easier to solve these problems in the unweighted setting. Say even like max weight matching, max cardinality matching is easier than the max weight setting, but they capture the heart of the problem, the unweighted problems. But then you often have to do some additional work to extend anything from the unweighted setting to the weighted settings. And there are like a bunch of problems for which this extension can we convert an unweighted algorithm to the weighted setting. So firstly, like let's look at a simple way of extending any weighted problem, like unweighted algorithm to a weighted algorithm. So this is the standard trick of bucketing. So the idea is basically, let's say like all weights are bounded by 1. This you can always assume after rescaling. Then I can make like log-n buckets. Like the buckets are like all elements which have weights between 1 and half and a quarter and 1/8, and so on. And any weight which is like 1 over poly and small, I can always ignore because they contribute almost insignificantly to the optimum. So hence you have log-n buckets or like log-n levels, you may call it. So any solution is basically sitting at one of these log-n levels. And now the one way of reducing the weighted problem to the unweighted problem is you just uniformly at random choose one of these log-n levels or like one of these buckets uniformly at random. And on average, like whichever bucket you choose, if you look at just the unweighted level problem at that bucket, because notice all of them have roughly the same weight up to a factor 2. So you might as well just run the unweighted algorithm there up to a factor 2. And this basically reduces your weighted problem to the unweighted problem up to a log-n factor, because you've chosen like one of these log-n buckets at random. So that bucket on average might have only like 1 over log-n fraction of the optimum. So the goal of our work is that when is this log-n factor loss wasteful? So as we'll see, like for many problems, in particular, these problems under uncertainty, prior works have basically performed this trick to reduce the weighted problem to the unweighted problem, and then they've designed some algorithms for this unweighted problem. So this is fine, but it loses an extra log-n factor. And the question we are asking is, okay, do we really have to lose this log-n factor, or can we save it? So to say it a bit more formally, like the three problems we'll be looking at will be under uncertainty. But all of them are under arbitrary downward closed constraints. The secretary problem, the profit inequality problem, and the stochastic probing problem. So in case you've not heard of these problems before, these are all like very well studied problems, having like tens or even hundreds of papers, some of them. And so maybe you can, for the rest of the talk, you might as well just focus your attention on, say, the first model, the secretary model. So the secretary model, you again have these n elements. So the elements, the downward closed set system, everything is known, but the weights are unknown. So the weights are unknown. The adversary chooses these weights or the values, and then these weights are revealed to you in a uniformly random order. So I'm going to reveal like the weight of some element. As soon as the weight of an element is revealed, you have to immediately decide, are you taking it into your feasibility set? It's an online problem or not. So If you take it, then you cannot drop this element later on. So you can only take future elements which are compatible with the elements that you've taken. On the other hand, if you discard this current element, then you cannot go back and pick it. The goal is what fraction of the hindsight optimum can I get? So again, you can study this problem both in the weighted setting and the unweighted setting. By weighted, I mean general non-negative weights, and unweighted basically means the weights are either 0 or 1. And similarly, like, so this was the secretary problem where the order is uniformly at random. There's the profit inequality version where the order is adversarial, but you have some distributional knowledge, and there's some stochastic probing, which is about adaptivity gaps. So all these problems have been greatly studied, even for general downward closed systems. In particular, what we know is that for all of these problems in the unweighted setting, we know that there's like a log-in algorithm, log-in approximation for all of these three problems. Here tilde is just hiding a log, like polylog log-n factors. So we know like roughly log-n is the right answer, both upper and lower bound for the unweighted part. This was known in like 10 years ago in Aviad's Stoch 16 paper for secretary and profit, and last year it was shown also for the adaptivity gap problem, the stochastic probing problem. But these are all for the unweighted settings. Trying to extend these results to the weighted setting, you can do the trick from the last slide, but this will lose an extra log factor, so you will get a log square n bound. And the main question we are interested in this work is like, when is this additional log n factor loss based? Like, can we save this log n factor, or can we not hope to save this extra log n factor loss? So is the right answer basically like a single log n or a log square n? Up to like, so we'll be sloppy about polylog log n factors in this work. And the interesting result we saw is that actually the results are not the same. So for some of these problems, you get like a log square n, and some of them the answer is single log n. And all of them actually can be understood, all of these results via the same approach, both the algorithms as well as the hardness, which we like with the principle, which we call the big decisions first. Where the idea is, which is somewhat like very quite natural in hindsight, is you want to make decisions for high value or high weight elements as early as possible. So ideally, we want to make high weight element decisions first and then the lower weight elements. What will turn out is that some of these models, like out of these three models, some of these models allow us algorithms which can go via this route, like they can make high weight decisions first and then the lower weight element decisions later on. And hence we can design better algorithms. On the other hand, for some of these models, this is not possible, and the adversary can basically exploit this to come up with a better hardness example. So this is useful both for better algorithms as well as better hardness. More precisely, for the secretary model, like which we're talking about, the random order, you can actually design a better algorithm. So the right answer is a log-in comparative algorithm. It's not log square. You can design a better algorithm where roughly the idea is that random order, because the elements are coming in a random order, you can be selective. Like in the beginning, select only high weight elements and then gradually go to lower and lower weight elements. And by exploiting this thing, you can get a log-in, like a better algorithm. On the other hand, for profit problem, where the arrival order is adversarial, there's actually a better hardness. There's a log square in lower bound. So log square is roughly the right answer. And similarly for adaptivity gap, also there's a log square in lower bound. So all of these results, they're all tied up to some polylog log n factors. But yeah, the main point is that the same principle, big decisions principle, what we call big decisions first, allows us to design better algorithms whenever they're possible, or like they help us come up with a better hardness example. So in the rest of the slides, I will give you like a high level overview of the techniques that go behind this. So firstly, let's start by recalling like how do these prior algorithms, the unweighted algorithms, work? Like how do they get like a roughly like a log-in approximation ratio, and why they don't easily extend to the weighted setting? And like that's why do we need to do more work? So in particular, like these prior unweighted algorithms like Aviad's work or this last year's work of Lee, Liu, and Zhang. So the high-level idea of all of these algorithms is, because these are some stochastic problems, you basically try to get a sample from the underlying distribution. So in the secretary problem, for instance, when elements arrive in a uniformly random order, you just discard the first n over 2 elements, half of the elements. And I mean, that only contributes roughly opt over 2 values, so you can ignore them. And now this gives you some kind of an unbiased sample from the underlying distribution. On the other hand, for some other stochastic problems like profit inequality or the stochastic probing problems, you know the distribution, so you can just literally take a sample from the underlying distribution. So the idea of these algorithms is like, okay, first you like take a sample or hallucinate a sample from the underlying distribution and then run some kind of a greedy algorithm. The greedy algorithm will basically satisfy two properties. It has to be, first of all, it will select an element if as long as it's feasible. Notice we are in the unweighted setting, so here maximizing the size is the same as maximizing the weight. So we'll select the next element if its weight is 1, as long as it's feasible, as well as it gets some good value compared to the sample. Like it kind of needs to have, it should not be the case that taking this element basically forces me to like drop all the other elements from the sample. So you want to say that it performs well and it's compatible to the sample. So that's the high level algorithm. So actually the algorithm is not that difficult because it's somewhat natural, it's some kind of a greedy algorithm. What's not obvious a priori is why this algorithm would work. Like why is it not overfitting? Because initially the sample is an unbiased sample from the underlying distribution, but gradually as your algorithm selects more and more elements, it might be overfitting to the underlying sample. So it's not clear. And the main idea of their analysis of these prior works is somehow to argue that you're not going to select any bad set or any set which has small size. And so what they basically argue is that, okay, look at any particular, any fixed bad set. You want to say that this is not going to be selected. Like you want to say like, okay, my algorithm is already fixed. I want to argue that the probability that my algorithm outputs some set which is of very small size is going to be tiny. And how do we do that? We first argue that for any particular small set, the probability that my algorithm outputs is going to be exponentially small. And then I'm just going to take a union bound over all such small sets. And notice that the number of small sets, the second observation which is crucial is that the number of small sets is also not so bad. It's like exponentially good. So because the number of small sets, they have size at most opt over log n, if I'm shooting for a log n factor approximation, and hence you have like only n choose opt over log n kind of choices, which is xpin opt, and you get a concentration in step 1, which is of e to the minus opt. So you multiply them, and that's the proof works. So all this is good for the unweighted setting. The challenge in extending this approach to the weighted setting is primarily like these two things are not going to be compatible with each other. So like the challenge already appears even if you have two weights. So let's say you only have two weight classes, and let's say one of them is high and the other is low. High weight elements, let's say they're like say something like square root and factor larger than the low weight elements. But both of these weight classes, they have roughly the same contribution to the octet. So the number of low elements will be like root and factor more than the number of high weight elements. So the number of lows are large. The number of highs are small, but their contribution to oct is comparable. And now the challenge becomes that, okay, if you look at from the perspective of these high weight elements, you can again argue this concentration that we had like in step 1 above, that you'll have like anything bad will be rejected with like e to the minus high kind of a probability, e to the minus omega high. But the number of bad sets has become much larger now because there are so many low weight elements. And if you select any of them, that could hurt a lot of the high weight value. So all of them you have to take a union bound. So the number of like these bad solutions has become much larger, whereas the probability hasn't gone so much, hasn't increased so much. So you cannot just like literally multiply and take the union. And indeed, like I mean, such an approach would not work because it would have otherwise given us a good algorithm for all the three settings. So like somehow this is the underlying approach. This is the most technical slide. So what we come up is like we show like basically that okay, how to overcome this in one of the three models, and the others basically this is actually a fundamental barrier. So let me give like a high level idea of the first theorem first, like how do we go about designing a better algorithm for the secretary problem. So in the random order version, the secretary problem, you can actually get a better algorithm. And this, by the way, also extends beyond weight, like linear functions, even to like some XOS functions. But the main observations on which it relies, I'm just going to discuss the observation. The first observation is that if somehow we could have magically chosen these elements in decreasing order of their weights. So like you have these high weight elements, you have these low weight elements, you have like maybe further lower weight elements. Let's say you just have two weight classes. So we want to design an algorithm where somehow we are only first making decisions about the high weight elements, and then we are making decisions about the lower weight elements. So you don't want to kind of crisscross them. High weight elements are first, and then the lower weight elements. If somehow we can magically ensure this, I mean, how we ensure that is a separate discussion. But if we can ensure this, then we are in good shape because now the number of bad sets, or like the number of small, like these things, now it reduces to exponential in high instead of exponential in low. So when from the perspective of the high weight bucket, you are good because you're getting a e to the minus high kind of concentration. And the number of such solutions is e to the high because when you're talking about these high weight elements, none of the low weight elements has been still selected. So they will not be contributing to your bad sets. So the number of bad sets has dramatically reduced. On the other hand, when you're thinking of from the perspective of low weight elements, although high weight elements have been selected before, the number of high weight elements is much smaller than the number of low weight elements. So even if you multiply these things, it's still like comparable to the number of low weight elements. Hence, you can afford to take a union bound of over all of them. So basically, if you can somehow go in the decreasing order of weights, these union bounds can be made, at least at an intuitive level. And that's the first underlying intuition. The other thing is, okay, like in the random order problem, although we are not going in decreasing order of weights, we want to somehow say that, okay, we can still mimic this as if we are going in decreasing order of weights. And this is where we kind of like, again, use the intuition, like check out, like, I mean, there's not black box, but roughly Aviad's algorithm, to get this, the unweighted algorithm of Aviad from 10 years ago, it kind of only needs to consider 1 over log n fraction of the stream. So it doesn't need to look at the entire stream. So building on this intuition, the idea is basically, okay, you like first again discard the first half, then use the n over log n next elements to first get all the high weight elements. Let's say like these are elements of weight. Now use the next n over log n elements to get all the weight half elements, then 1/4, 1/8, and so on. So the point is now, although the stream is not coming in decreasing order of weights, our algorithm is going in this order. Like it first selects only the high weight elements, then it goes to the next weight elements, and then it goes to the next weight elements, and so on. Because these weights are now decreasing in order, now you have the property that whenever you're talking about a weight class, it can afford to take a union bound about over all the like high weight elements that appeared before that you've selected. And you don't have to take a union bound over the later ones because your algorithm hasn't selected any of them yet. That's the underlying intuition. The precise details have to be like get done very carefully. Now let me similarly give like a high level idea of our hardness examples. So like how to go about proving like lower bounds for profit and the adaptivity gaps. And here maybe it might be good to first recap the unweighted, like the hardness, the log n hardness for the unweighted problem. So this is due to like already the work of Babayev, Mollica, and Kleinberg, where they introduced the secretary problem, the matrix secretary problem. And so they showed like that for the unweighted problem, you have a log n hardness. And roughly their hardness is based on the following idea. Like you have n elements, partition these n elements into n over log n blocks, where each block has roughly log n elements. So you have like log n elements in this piece, log n elements in this piece, log n elements in this piece. The point will be the following, that the feasibility constraint will say that it's an arbitrary downward closed system. It will say that you can only select elements from the same block. So you cannot be in a situation where you select like one element from this block, one element from another block. So all the elements that your algorithm selects has to be from the same block. And now, like if you reveal the weights of these elements are chosen such a way that in expectation, any block has only one element. So in particular, like each element has weight 1 with probability like 1 over log n, and otherwise its weight will be 0. So this is the stochastic distribution. Now the point is that because there are so many blocks, you can argue that in hindsight, there will be one of these blocks of size log n, where all the elements are active, like all of them take value 1. So opt is going to be roughly like log n, like log n over log n, whereas any online algorithm, which kind of takes the first element in a block, it's committed to that block without seeing the rest of the elements. And out of those remaining log n elements, only like in expectation, one more will realize. So any online algorithm will have value like at most 2-ish, whereas the hindsight optimum is omega log n. And that's the underlying intuition why there's already a log n hardness for the unweighted problem. And now let me say like how we roughly increase or like boost up this hardness using weights from log to a log square. The higher level idea like of a hardness result, like this log square and hardness, is to put this unweighted hardness in some kind of layers. So you have like a layered structure. So the topmost layer is basically the hardness example from the last slide. But now I'm going to attach some values to them. So think of these are low values. The next layer will again have such an instance. A third layer will again have such an instance. As you go lower, the weights increase. So basically, like these elements, let's say, will have like weight 1/8, these will have 1/4, these will have half, and so on. So the lower we go, the weights increase. And the point will be roughly the following, that any online algorithm, so the arrival order will actually be the increasing order of weights. So you first get the low value, all the elements one at a time, then the higher next, and so on. So any online algorithm, basically, as soon as it takes some elements from one of these blocks, it's committed to that block. My downward closed feasibility system will allow me to take elements from a single block or a root leaf path. Like basically from any blocks which are on the same root leaf path. That's my downward closed system. Now the online algorithm, as soon as it takes like a few elements from any of these blocks, it is committed to this particular block as well as this particular path. Hence, you can argue that because it has committed to it, it cannot get too much value. It can basically get like whatever value it basically got from this single block here. Like in expectation, you won't get any value above, or like only constant value above. Whereas the offline algorithm will actually go, the hindsight optimum will go actually look at the highest value elements, then check out its children, like whichever has the highest value, go into that subtree, then go in this other subtree, like based on the higher values. So such kind of a greedy-ish solution, but going in the opposite order, going from high values to low values, you can argue that you can get like a lot of value from every layer. So the hindsight optimum will be very large, whereas the online algorithm will only basically get one of these layer values. And because each layer will contribute roughly the same value to opt, so you also suffer an extra factor of the number of layers, which is log. So that boosts this log n factor from the last slide to log square n. The catch, however, is that, okay, if you try to mimic such an approach as given, the number of elements you will end up getting is like exponential in n. So the number of leaves that I would need is going to be exponential in n, whereas we wanted poly n elements, because like log n, when we say log n, it's n is the number of elements. So naively, this will not work. The idea to make this work is to use some kind of a double error correcting. So rather than having these blocks totally disjoint from each other, what we end up doing is that, okay, we have these blocks which have overlaps, like these elements are not fully disjoint. But using an error correcting code, we kind of say that, okay, most of them are like basically disjoint. So they have overlaps, but the overlaps are so small that they are basically going to be small error. So we'll use two error correcting codes. One is to encode that, okay, within a layer, like these blocks are basically disjoint. The other error correcting code is to ensure this root leaf path. Basically, again, like once you take elements from a single thing, a single block, you are kind of committed to the single root leaf block. You cannot take from another root leaf path. So making this like, yeah, requires a little care, but yeah, again, that's the underlying intuition to boost up the hardness from log n to log squared n. And I mean, like, a variant of this construction works for even adaptivity gaps. And the details are changed because of the problem structure, but like morally, it's the similar kind of idea to show a better hardness for this adaptivity gap. Good. So to summarize, what we saw basically in this talk is these three different problems: the secretary problem, the profit inequality, and this stochastic probing problem. All of these problems, like this, was this log n versus log squared n gap, because of this, like this simple trick of reducing the weighted problem to the unweighted problem. And it was not clear previously, like what's the right answer. So what we can show is that, like, basically for the secretary problem, you can exploit this big decisions first, like go in decreasing order of weights, and that allows you to get a better algorithm. Whereas for the other two problems, basically there is like the adversary can kind of exploit this fact, whereas your algorithm cannot go in decreasing order of weights, and hence you incur a large hardness. So this big decision first idea is useful both to design better algorithms as well as a better hardness. And some of the open questions is, one is like, okay, like some log n factors are left open in our work. Like, so we are able to resolve like log versus log squared, but there's still like some log squared kind of gaps left. And resolving these log n is like a little bit tricky. For instance, like to give you another related problem is the matroid secretary. Like rather than working with general downward close constraints, what if I had shown you that this is a matroid? So the famous open question there, the so-called matroid secretary conjecture, is that for the unweighted problem, there actually you can, like, greedy algorithm is already optimal. So it's like one competitive. But for the weighted setting, currently the best known algorithm is a log n, and it's unclear what's the right answer or like how to get it. So that's again the question about like resolving one of these log n's. That's another related question. And more broadly, I guess, yeah, so we're interested in using this big decisions first principle for other applications, and there it could be very interesting. That's it. Thank you.